Welcome everyone to the first Atto Fridays Seminar from 2026. In fact, we started 2021, so it has been a while. And it's a pleasure for us to have Dr. Jan-Marcus Dahlström. He is an associate professor at the Mathematical Physics Division of Lund University in Sweden, where he is a Wallenberg Academy Fellow since 2019. And previously, he has worked as a postdoc researcher at Stockholm University and the Center for Free-Electron Laser in Hamburg. He defended his PhD in 2011 from LU and under the supervision of Professor Anne Louillier, making early contributions to the interpretation of attosecond time delays in photoionization and to in situ measurements of high harmonic generation. And currently, his research focus has shifted to time-dependent strong coupling phenomena at short wavelengths in connection with free electron laser experiments. So we're really happy to have you here. And we heard also he is an Atto Fridays fan, so we thank him and his group for watching. And today he's going to talk about time-dependent strong coupling phenomena at XUV wavelengths. So the floor is yours. Thank you for joining and welcome everyone to the Atto Fridays.
Yeah, thank you, Carla, very much for the invitation. And this is such a pleasure to be here. Now, today I want to tell you about the research that we have been doing in the last couple of years on time-dependent strong coupling phenomena at extreme ultraviolet wavelengths. So it's sort of all about electrons and ions and photons interacting with each other. And we use short laser pulses that are available with free electron lasers to do ultrafast coherent control. And then during this talk, I will show you how then spontaneous decay processes of the ions that we generate can lead to a transfer of entanglement from the electron and ion to the electron and the spontaneously emitted photon. This is the goal of my presentation, to go all the way, so to speak. And there's a bit of attosecond physics in this for sure. So this is my group, or this was my group, I should say, because this group picture is a few years old. But it is still true that we are interested in attosecond physics, ultra-fast entanglement, relativistic dynamics by solving the time-dependent Dirac equation, and then lately very much problems of strong coupling in atoms. Today's talk, I will focus on work done by Axel here. He is defending his PhD thesis later this year. So. And we're not the only people who are interested in strong coupling. In fact, strong coupling is at the foundation of light-matter interaction between atoms and photons. So we know that strong coupling refers to Rabi oscillations in a two-level system. So we can go from a ground state to the excited state and back in this way. And Knight predicted in 1977 that if this atom is ionized, then in fact the photoelectrons that are ejected will have two peaks in their kinetic energy distribution, which is separated by the Rabi frequency. This phenomena was then later looked at by Rogers and Levenstein to include the effect of a smooth envelope. And then beyond these two peaks that I show here, one sees additional rich spectral coherences and fringes in between. In the 90s, it was possible to solve this problem by solving directly the time-dependent Schrödinger equation for the hydrogen atom. And then it was found that these two peaks are not equally strong. In fact, when the field is strong, we tend to see asymmetries of these two peaks. Even before this, we had the work of Beers and Armstrong describing how a two-level atom interacts with intense light and including coupling to the continua. This was done by effective Hamiltonian theory, and they predicted nonlinear decay processes affecting the atom. This theory with effective Hamiltonians, I revisited with my PhD student Edwin Olofsson, and we identified that the asymmetries that could be seen in this doublet were related to a stabilization effect of the atoms going back to the work of Beers and Armstrong. Today, I will not focus on this two-level cycling atom, which is photoionizing, but rather we will consider an atom that is photoionized, and then there's a strong coupling in the ion between two different ionic bound states. And it was predicted by Grobe and Eberle in the 90s that if you photoionize an atom and then have this strong coupling in the ion, then the photoelectron will also show two peaks. And these peaks would be separated by the Rabi frequency. So what is going on here? There were some experiments actually following closely after this on alkali atoms. But in alkali atoms, it's difficult to isolate this kind of simple system with a two-level system, because as you increase the intensity, typically other states get involved. So, and then theoretically, this was looked at again by Sang and Rohringer, including effect of smooth envelopes, and they improved the interpretation here, including, again, more fringes here due to the envelopes. And then they said that these fringes should be related to how many Rabi cycles the ion is doing. But then you and Mattsson looked at this, and they looked at the case with two pulses. And then they saw that they just get very complicated photoelectron spectra here, and concluding basically that, there's much more that one can understand about these things. And this is really my motivation for going into this type of problem now, to try to understand how we can control the photoionization mechanism with the coupling in the ion. So why are we interested in this also is because we now have very available free electron lasers with high intensity and short wavelength. So as a theorist, this cartoon is kind of enough as a motivation. But on a more serious note, together with Saikat Nandi, we had the pleasure to work and interpret experiments from the Fermi FEL, where we have the high intensity and the short wavelength to drive Rabi oscillations in neutral atoms like helium, here between the 1s and the 4p. So the first experiment that we worked on was in the neutral helium atom and observing strong coupling. So in the experimental data, one can see this avoided crossing here between the photoelectron line here. As we're increasing the photon energy, we're increasing the kinetic energy of the electron, but then when we hit the resonance, we see a splitting. So this is the signature of strong coupling. It says that the Rabi frequency is bigger than the decay that we would have in the atom. So we have reached this sort of night doublet picture. But looking in more detail, we realize that there are nonlinear ionization processes going on. So the ionization rate from the excited state is comparable to the ionization rate from the ground state. And these two quantum pathways then lead to quantum interference. And in fact, this is causing a strong asymmetry in the doublet. Actually, one of these tones or night doublet peaks can even disappear, in which case we enter what we call the dressed atom stabilization regime of the atom. I will return a little bit to this at the end of my talk, but first I will spend more time to talk about the Grobe-Eberle type of doublet, which is the time order reversed process where we first ionize the atom and then we drive the ionic transition. Here, experimental data was taken and it was published in 2024. And the data is a little bit noisy, so we needed to look at this and clean up the data, remove background. And when we did that, we could see a very clear avoided crossing here as well. And in order to understand what is happening in this Grobe-Eberle doublet formation, we used the theory of entanglement to quantify quantum correlations between the photoelectrons and the ions. So in this particular case, we have a helium ion, and we're driving the transition 1s to 2p. So 1s and 2p and back in this way. It's also important to stress that in both of these experiments, it's a single free electron laser frequency that is driving all the processes. So it's the same photon that ionizes here that then creates the coupling here. I mean, it's the same frequency that is doing this. So is photoionization spooky? I mean, why are we talking about quantum entanglement when we talk about photoionization? Usually when we think about quantum entanglement, we encounter wave functions like this one. This is one of the Bell states. It's a maximally entangled state. We have some qubit, some red qubit, and some blue qubit. And we say that it is entangled because the wave function cannot be factorized. So the red part cannot be factorized with the blue part in this way. In our experiments and our theoretical ideas, we don't have two qubits. The red part is more like the internal states of the ion, which we can call little a. And the blue part is more like the electron kinetic energy, which is a continuous variable. So why do we need quantum mechanics to describe this? Everyone knows that we can use photoelectron spectroscopy and that we have different probabilities for having an electron with a certain kinetic energy and an ion in a certain state. This is just energy conservation, and it can be described by this classical density matrix. Diagonal density matrix. So for that, I just want to say that nature isn't classical, damn it. It's a famous quote. And this kind of density matrix we would get, but only after our ion and electron have completely dephased with the environment, meaning that all coherences in the system have vanished. And remember, we're looking at an ion and an electron. So how could we possibly keep track of one electron in an environment so that it's completely dephased? I think this is beyond our control. So our philosophy for looking at entanglement in photoionization is really to start, we use pure states, and we consider the complex time-dependent wave function of this composite system. It contains an ion and an electron, and together we solve the time-dependent Schrödinger equation. And when we have the wave function, we can construct the density matrix and apply the von Neumann entropy or some other measure of entanglement. And then we can analyze the wave function in time. We want to understand the properties of the wave function as it develops. This is our goal. And entanglement in this case, it really means correlations between the particles. And it's not the classical correlations that you would have here in the density matrix here, but these are the quantum correlations, which are basis independent. They're a more abstract and fundamental property of the wave function. And we have a clear partition in our problem because we have electrons on one side and we have the ions on the other side. So let me just rant one more time. Photoionization is quantum. We know that already because we have studied the phases in photoionization, seen interference effects, measured coherences by methods like Rabbit and Kraken. And for me, to go into and understand how we can apply techniques from quantum entanglement or quantum information, I think the work of Arosh and Raymond is very useful, and these topical reviews by Butch Leitner, for instance, is a very good place to look. So we want to go from sort of the simple photoionization domain, the photoelectric effect, where we have energy conservation by field-free states, sort of creating this line here again with we increase the kinetic energy because we're increasing the photon energy. This would be the domain down here. And our reaction is simply helium goes to helium plus and an electron. But if we increase the intensity and if we're resonant, then we can cross the Rabi period here in this parameter space. And then we can start to have energy conservation instead with dressed states. So now the helium plus is strongly coupled between the 1s and the 2p. The yellow dots here are from the experiment performed by Saikat Nandi and collaborators. So why would it be more interesting or more quantum to study these ion couplings? Well, the one point would be that now we really have something that looks much more like atom-photon pictures because we're in the strong coupling regime. So we're dealing with dressed states. And the other case is that it's easy to create superpositions now in the ion that are entangled with the photoelectron. And this is something we're going to see and explore here further in the talk. So the dress state picture. Now, first of all, if we just have a particular binding energy here for the ion state A, then of course, when we ionize a photon, we would go up to this kinetic energy here for the electron. But when we have dressed states, they depend on the intensity of the field. So if the pulse is here, we would typically bend down and control the binding energy of the atom. So we can call this dressed state plus. It has more binding energy, so the kinetic energy here is lower. And then we have also another dress state, the minus state, and it has less binding energy, so we would create an electron with higher kinetic energy. This is nothing but the Grove-Eberly doublet, or if you want, you can call this an Ortler-Tones doublet. It is an Ortler-Tones-like splitting here with a Rabi frequency in between. So now we want to study the quantum entanglement that we generate by ionizing with these dressed states. We have our two peaks here, the low kinetic energy peak and the high kinetic energy peak. And we can look at the ionic channels of the free ionic states, so state A and state B. And then we see B is blue. It has the same contribution to the high energy peak as to the low energy peak. So if we try to do classical correlations of the ionic states with these kinetic energies, we would always find some close to 50-50 probability of detecting in coincidence the ion in A or the ion in B. So we would see no classical correlations. Looking at this for the first time, it is not clear then if this would be an entangled wave function or if this would just be a mixed wave function. And in real experiments, this is an important question because we don't know. But in the theory, with a single atom, we know that it must be entangled because we have a wave function. So what we need to look at now is the relative phase that we have in our ionic space connected with the kinetic energy E. So for the high energy peak, so looking at electrons with high energy, we see that the relative phase in the ion would be minus pi/2. And when we look at the low kinetic energy peak, we instead see a superposition with plus pi/2. So there's a difference of pi between the coefficients for B, meaning that we have two orthogonal ion states and that we have entanglement. In fact, we would have complete entanglement because we have really orthogonal states. So in order to quantify the entanglement that we have, we can use measures of entanglement. And the von Neumann entropy is one example. We calculate it, and we see that from the beginning, if we have a very short pulse that doesn't have time to create the strong coupling in the ion, then we will not have any entanglement. The value is 0. But as we make the pulse longer, we will have time to couple the ion, and then when we pass one Rabi period, then we will have achieved a value of 1. Which is the maximal entanglement that we can have for an ion that's described as a qubit, two-dimensional. So in more detail, the von Neumann entropy measure that we use here is given here, where rho red is the reduced density matrix of the ion. But the property that we have here is that we could also use the reduced density matrix of the photoelectron, and it would generate the same result. We choose to use the reduced density matrix of the ion because it's two-dimensional, so it's much easier to handle. So in conclusion here, we create full entanglement, maximal entanglement between the photoelectron and the ion when the pulse is longer than one Rabi period. If we include a shaped pulse envelope, then it's more correct to say that the pulse area should be greater than 2 pi. In quantum optics, we use pi pulses and 2 pi pulses and pi over 2 pulses. So this is the lingo one can use. So we would have full entanglement, but as we saw on the previous slide, we still wouldn't see any classical correlations when trying to detect electrons in coincidence with the state of the ion, A or B. So this is not at all a contradiction, but rather a property of quantum correlations. They depend on which basis you use to do your measurement. So we need a 2 pi pulse to create full entanglement. What if we just take our 2 pi pulse and we split it up into 2 pieces, a pi pulse and then another pi pulse? This is done here. So here's again the entanglement, the von Neumann entropy. It starts out at 0. Then we ionize. The entanglement goes up to 50%. And then the second pulse comes, and now it goes up to 100%. So we have the same conclusion if we distribute our area into 2 pulses. However, we can do more. We can control the phase between the first pulse and the second pulse by coherent control. Now, the second pulse, when it's tuned out of phase, then it will not generate any further entanglement. So in this way, we can coherently control the amount of entanglement that's being generated between the photoelectron and the ion, even though we have a longer interaction in time. We can continue to play with this infinitely many times, but let's just take the case with 3 pulses. These 3 pulses add up to 2 pi. So if they're in phase, then we can increase the entanglement, then we can increase the entanglement, and then finally increase the entanglement up to close to 100%. But by changing the phase of the second pulse, we can make it so that the entanglement doesn't increase during that pulse. And then again, we can choose if we want to increase it or if we want it to keep it steady. So as you can see, with the von Neumann entropy, we get a very clear picture of how the ion and the photoelectron are quantum correlated just by these curves. This should be compared with trying to understand what the actual photoelectron distributions look like for the 2 different ions. So here you see the dashed one and the blue one corresponding to the ionic channels. Sometimes they don't overlap, sometimes they overlap. And also the colors that you see here are the relative phases in the ionic superposition. So it really is very complicated, as I advertised on one of my introductory slides. But with the measure we do here, we can clearly see that once entanglement is generated, it cannot be undone, or maybe a little bit it can go down, but not much. We certainly cannot make it go all the way down. But we have found that it is possible to control it in such a way that we can halt it so that we have more interaction, but it doesn't increase further. Don't take this analogy too seriously, but we know from the second law in thermodynamics that we can only increase the entropy in an isolated system. So I think there's a little bit of a connection here, but we shouldn't take it too seriously. So the next question that I'm going to ask is if we can actually reveal these quantum correlations now, because we saw that actually we didn't see any correlations when trying to measure in coincidence in the preferred basis of the electron and the field-free ionic states. The trick that we're going to do now is that we're going to use coherent control, and we're going to use 2 pulses, or rather, we're going to use 1 pulse, but then we're going to abruptly change the phase of this pulse in the middle. So this is the envelope. Here the electric field is oscillating in one way, but here the electric field jumps by pi and it starts oscillating in the other way. Such an envelope is really an approximation to 2 pulses, and it's our theorist's choice to work with here. You can also think about it as 2 Gaussian pulses if you want. What happens physically is that if we have a Gaussian pulse, then we will induce, in a 2-level system, we would induce Rabi oscillation. So the population in the ground state would go down, and then it would go back, and then it would go down. But when we induce this phase shift, then we can think about this on the Bloch sphere. And on the Bloch sphere, there's something called the torque vector, which determines how the state will rotate on the Bloch sphere. And when we introduce a phase shift of the electric field that's driving the process, the torque vector is reflected, and all the Rabi oscillations will start going backwards. So now, rather than continuing here, it would just go back to the original place. This is a property also for 0 area pulses, which also have a phase change in them. So we see this reversal of the Rabi dynamics in the ion. And then finally, the pulses that we use, we're not just considering the 2-level system, but we're actually ionizing helium, and then we're generating the helium ion and the electron. And we don't completely saturate the helium atom. We only ionize it by maybe 10 or 20%. So in order to look at the photoelectron and the ion wave packet, we condition on photoionization, meaning that we just disregard the part of the wave function that is related to the ground state. This is to have a clean partition between ion and photoelectron. So what do the photoelectron spectra here look like? So if we do just the Gaussian pulse, then we have similar to the results of Zhang and Rohringer. We see these 2 Gros-Beverly doublet, and then we see some fine interference structure in the middle. When we have our Gaussian with a phase shift in the middle, then we just see 2 blobs here, 2 lines, similar to the Gros-Beverly doublet, but all these fine interference structures actually disappear. This is when we look at the total photoelectron signal, where we include the ion state A and ion state B. If we resolve over the ionic state, so this is the channel A and this is the channel B, then in the case of a Gaussian pulse, it looks very, very similar. You have the Gros-Beverly doublet, the doublet here, and then you have some interference fringes in the middle. But when we have our phase shift in the driver, then we instead get these curves here that bend in such a beautiful way here. And when we look in detail about this, we see that on this structure here, on this fringe, we have photoelectron probability. But in the other channel, we have a dark region. So that means that the photoelectrons in the two different channels are avoiding each other. And this, of course, opens up to do coincidence detection of correlations between the photoelectrons and the ions in a way that we can now completely coherently control. So seeing this avoided phenomena in the calculations didn't mean that we really understood it at first. So I will try to explain it now with some PowerPoint animations so that you can understand where this avoiding phenomena is coming from. This quote here, if you can't explain it simply, then you don't understand it well enough. This is a quote that according to the internet, Albert Einstein may have said something like this at some point. Okay, it's a good quote. So let's understand this avoiding behavior. We have address state binding potential energies here, and we can ionize from the minus state. It will take us to the high kinetic energy. Now, what we're going to do is we're going to take our two-level Hamiltonian for the ion, and we're going to change the sign of the electric field. When we do that, we will actually keep the same eigen states, plus and minus, as before, but what will happen is that the eigenvalues will flip. So the plus will now become minus, and the minus will become plus. That means that after we do the sign flip here in the middle of the pulse, then it is this state that is the minus superposition in the ion, and it now has higher binding energy. So now if we ionize from here, we would go to a lower kinetic energy. It is also possible to ionize from this state, which is the plus state. This now has low binding energy, so it goes up to the same kinetic energy. But we now have a contribution from two different addressed states, the minus state and the plus state. So what does that mean? Similarly, here to this one, we will have the plus and the minus contributing to the lower energy. What we need to do is we need to add coherently the plus and the minus, and adding plus with minus the address states, we actually get back the field-free state A. And if we add them together but with a minus sign, so a different relative phase, then we get B. So depending on exactly what kinetic energy we get here in the high kinetic energy part, then we will isolate, we will entangle the field-free ground state or the field-free excited state. So they're avoiding each other in our way of thinking about this. The same thing happens here with the lower kinetic energy branch. If you don't believe in PowerPoint proofs like this one, we also did a saddle point analysis and show explicitly the cosine and sine dependence. This is the amplitude for the photoelectron from the ground state, and this is the amplitude for the photoelectron from the excited state. And here you can see the sine function, and here you can see the cos function. And of course, when we square these to get the probabilities, we get this trigonometric identity where they're sort of filling in each other's places. Great. Okay, so the next question is how we can control the entanglement manifestation. We understand that by changing the phase between the two pulses that we have, now again I consider two Gaussian pulses that are separated in space, but let's make them long, let's make them 5 pi. That means that already, because this is a pulse that's longer than 2 pi, we will have full entanglement generated here, and then we will come with a second pulse, and we will still have full entanglement. But actually, what we can do is we can change how the photoelectron distributions look like. So if they're in phase, then we call this a plus and a plus pulse. Then we just see an interference pattern here that's That's Ramsey-like interference because we have coherences between these two pulses. But the two channels, the alpha channel and the beta channel, the ground state and the excited state, they look the same. So you wouldn't be able to see any coincidences here, detect any correlations, between the two channels. On the other hand, when we change the phase of the 5 pi pulse to minus, so we have plus and minus pulse, then we see this avoiding behavior, and we clearly see the correlations between the two channels. I want to stress that in both of these cases, the ion and the electron are fully entangled because the pulse area is bigger than 2 pi. It's just that in the experiment, one can detect correlations or one cannot detect correlations. So how do we quantify this difference in seeing correlations and not seeing correlations? We're proposing something we call amplitude entanglement. And what we're doing is we're taking our wave function of ion and electron, and we're just removing all the phase information that it contains. I'm going to show you a little bit later, but the result is that this pulse here, which has no correlations, gives the blue curve here, while this case, which clearly has correlation, gives this curve here. So we can see how, because of the second pulse, which has a minus phase, a pi phase, we can see how it goes up and we reveal the correlations. But there are also details happening earlier. For instance, we can see that during the first pulse, the entanglement, the black curve, it increases quite fast up here to the 2 pi mark where it's fully entangled. The amplitude entanglement is much smaller, and it only increases a little bit later. It's small in the beginning because when we have short pulses, they don't have enough time to Rabi cycle. And if we have a short pulse that is only a pi pulse, then actually the envelopes of the photoelectrons will be almost identical. This is the alpha and the beta channel. So the entanglement that's generated here is due to phase differences between the two different channels, not amplitude. And that's why we have entanglement, but we don't measure it in the amplitude entanglement. What's going on with this 2 pi? Why do we see a sudden rise in the amplitude entanglement for 2 pi? If we consider a pulse that is 2 pi, and then we look at the photoelectron distributions, then we see that from the ground state, the blue curve, we actually have a doublet. Here we can see our Otler-Tones doublet or our Groh-Beverly doublet. But from the excited state, we only see a single peak. So we can distinguish the two channels, the ground state and the excited state, by their amplitudes. And that is what this signal is implying here, the 2 pi peak. There are also some smaller peaks at 4 pi and so on, and these are due to structures that appear in between the two main peaks. That would be much more difficult to resolve. So this amplitude entanglement, which we call S-eta, it gives us information about what correlations can be observed in a preferred basis. So without having access to performing more phase measurements. And how we're doing it is that we're taking the full density matrix, and then we're tracing over the photoelectron. But before doing that, we take the absolute value of the full density matrix. Intuitively, I understand what we're doing in the following way. I mean, calculating the von Neumann entropy gives us information about how entangled the particles are. And if we don't allow them to have a phase to be entangled with, then they will not be able to be as entangled because it's only by the amplitude they could be entangled then. So in general, it would be so that the von Neumann entropy, the true value of entanglement, is bigger than the amplitude entanglement. Okay, and then coming to whether this entanglement actually could survive. all the things that I've been talking about so far has been the excitation on a femtosecond ultrafast time scale. Pulses are on the order of 10 femtoseconds. Now, what happens under ideal conditions? Well, if we wait for 1,000 times longer to the 10 picosecond time scale, then we would have a T1 type energy relaxation. We will have spontaneous decay of the ion. The B state will go to the A state, and we will eject a photon. So now we want to see if we can study how the entanglement is transferred from the electron and the ion to the electron and the photon, the spontaneously emitted photon. The question is how to calculate fluorescence. It's something that we hadn't done before in the group very much. And we found this paper by Mollo from 1975 called Pure State Analysis of Resonant Light Scattering. It's a wonderful paper. Basically, it's allowing us to do resonance fluorescence, but in the Schrödinger picture, so solving the usual time-dependent Schrödinger equation in a wave function formalism. In this way, we need to expand our basis from the ground state of the atom and these two ionic channels to also include the photon number and the photon modes. So we can emit one photon so that the ion goes down to its ground state A, and then we have ejected one photon into the mode L. Then from there on, it's possible to go up to the excited state B, and then one could again emit fluoresce a photon, and it could continue. And this is indeed the kind of physics that Mollo had in mind when doing these calculations for a two-level system. But in our case, the excitation that we have here is on tens of femtoseconds, and the decay channel here is tens of picoseconds. So we have very different time scales for the process. That means that actually we don't have to include photons that are ejected beyond the first one. And that we will really have, on average, we will have half a photon absorbed by the ion and then emitted. So here I show again the entanglement with the von Neumann entropy. And the first curve, the blue curve, this is the electron-ion entanglement that I already showed you. It starts at 0, then it goes up to 1, which is the maximal value for the qubit. It continues to be 1 for a very long time until we reach the time scale of spontaneous decay, at what point it goes down to 0 again, because now the ion decays to the ground state, and there it will remain. If the ion is determined in the ground state, and it can be factorized out, and it will no longer be entangled with the rest of the system. We do a similar thing looking at whether the photoelectron is entangled with the photon number. So we put our partition so that the electron kinetic energy is on one side. We condition on the on the ion being in the ground state, and then we see if we have one photon, which or no photon. When we do this, we can see that the entanglement rises on the time scale of spontaneous emission, and it goes to 1. So this is a transfer of entanglement between two types from the ion to the photon number. We can again put our partition so that the photoelectron kinetic energy is on one side, and then on the other side we now have the full system. We have the state of the ion, A or B, and then we have the photon number 0 or 1. So in total, this would be a Q-quad, a 4-dimensional quantum object. And we can see how much entanglement there is between the photoelectron and the Q-quad. We see that in the beginning, it follows just the same as the electron ion, but then during the fluorescence period, here we have an entanglement that is bigger than 1, meaning that the entanglement is larger than what we would have for the qubit. So here we have really electron entangled with an ion and photon at the same time. It doesn't go quite up to the value of a Q-trit, which is this one, the three-dimensional quantum system. So actually, if we don't include the delta state here, this is still a very good description of what happens. With this model, which is mostly analytical, we can also study how much information there is in the modes of the field, so the different values of L. And we find that over a long time, so when this happens, there is no such shared information. But when we are in the laser field, this is how long the pulse is here up to this gray line, then actually there is information in the mode that's being shared with the rest of the system, for instance, the kinetic energy of the electron. And this is happening because we're driving the ion with a strong field, and it's fluorescing with this Mollo-like three-peak or even more fancy structures. But as we let the ion decay, it will decay on a single frequency, and then again it will factorize. So this is a transient entanglement feature that we can control in this way. So to summarize these things here, I have showed you how we can control the entanglement in photoionization, and also how we can transfer entanglement in this electron-ion-photon system. And this is the key results here of Axel Stenquist's thesis that will be happening after summer. In my group, we've also looked at strong field effects beyond the Rabi model, or beyond the rotating wave approximation. This is work done by Jacob Brunke, studying giant counter-rotating oscillations on the attosecond time scale. We also studied stabilization now for a couple of years, as I mentioned in the introduction, by Edwin Olofsson. So we have discussed the photoelectron signature of dressed atom stabilization. I just want to show you very quickly what these two things are. So counter-rotating oscillations is this kind of fast oscillations that depend on the optical frequency. So here we have a two-level system, a ground state and an excited state. And in a two-level model, we would have these weak oscillations, and they would always be reciprocal in the sense that the wiggle in the ground state would be compensated by the wiggle in the excited state. Because these effects are typically not so strong in two-level systems with optical frequencies, they're usually neglected, and the Rabi model is very good. But if we consider a more realistic description of an atom subjected to an intense XUV field, then we will see much stronger counter-rotating oscillations. Here you see the ground state is barely shows any such fast wiggles, while the excited state shows very large oscillations here in the blue sort of shaded area. So they're very strong and they're non-reciprocal. The excited state is affected, but the ground state is not. And if we zoom in on this, we can understand our ab initio simulations also with a model. And there's very good agreement for how, on the attosecond time scale, populations are moving in the atom in the excited state. So this is really now an instantaneous electric field effect that is coupling the excited state to Rydberg states. So what we're seeing is a simultaneous atom-photon physics with the Rabi oscillations and an instantaneous field effect, so like strong field effects at the same time. And to measure such oscillations, I think, is a very fun and open challenge in attosecond physics. Finally, for the last part here, I just want to show you what we have done on the coherent control of ionization using stabilization. So if we have the same amount of ionization from the excited state and from the ground state, then we can block one of the dressed states. The dressed state with high energy will not ionize. We can use this in a 2-pulse sequence. So we consider one pulse and then another pulse, and we control the phase of the second pulse. If they're in phase, then we will just induce Rabi oscillations, which means we will populate the plus and the minus state at the same time. And then during the second pulse, the same thing will happen. Okay, we would ionize from the minus state here and from the minus state here, and not from this one. But by carefully tuning the phase between these two pulses, we can make it so that during the second pulse, we only go to the to the dress state plus. One can understand this again on the Bloch sphere by tuning the torque vector so that it becomes parallel with the state vector. Then we will not ionize during the second pulse at all. So this is a simulation, and here we can see the photoelectron yield as a function of time. During the first pulse, we will generate photoelectrons. This is the first pulse here. And then during the second pulse, depending on the phase we choose, we can suppress ionization, or we can even enhance ionization beyond how much we ionize during the first pulse. So this is an idea that we have submitted to perform an experiment at the Fermi-FEL, and we're waiting for hopefully good news about that. So in summary, I showed you an analogy here with entropy and thermodynamics, where we saw that we can increase the entanglement between electrons and ions using pulses to its maximal value. But then, but even when we have maximal quantum correlations between the particles, there are cases when we don't see any correlations in our measurements. I put a little star here because this is very important to say that when we're doing experiments, we're doing this in a preferred basis, the electron kinetic energy and the field-free states of the ion. So there's no contradiction here. And we also can halt the generation of entanglement using coherent control. So we can choose with the second pulse, add more photoelectrons and ions, but still don't increase the entanglement. Using coherent control, we can also alter the manifestation of entanglement and as they show up as correlations in our experiments. And finally, I showed you 2 examples of beyond Rabi or beyond rotating wave approximation strong field effects that I think would be really nice to study in experiments: non-reciprocal giant counter-rotating oscillations and addressed atom stabilization. So with this, I want to thank you for your kind attention, and I'm happy to answer questions that you may have.
So thank you so much for this really interesting talk. Are there questions, comments? So please raise your hand or write in the Q&A tab. Also, if you're watching on YouTube, don't forget that the live chat is open for subscribers. So if you are a subscriber, do write your question there, because we are monitoring as well, and we'll be able to reply. Before we start, I would like to make a few announcements. We are considering a new Quantum Battles workshop, so we're looking for controversial topics. If anyone in the community would like to reach out to us and make a suggestion, do feel free to write to quantumbattles@gmail.com and make your suggestion. We have our own ideas. We are brainstorming, but we are intending to organize a great tournament for next year, if we are lucky, and we are looking for suggestions from the community. So let me see. We have something here on YouTube. No, we just have one person saying that this was an amazing talk on our subscriber poll. So thank you for supporting us, and hello. Let me see now on Zoom. Nice talk. Yes. So we appreciate you watching. We had a lot of people also here today on YouTube and elsewhere. And how is this? Yu Hei. would like to ask a question. Go ahead. Hello, Yuhei. You
Hello,
can
can
ask
you
your
hear me?
question. Yes, absolutely.
Okay. Okay, very great talk. So I have one question regarding the giant counter-rotating oscillations. Actually, I don't quite understand it. Like, maybe you can remind me or explain a little bit more what's the difference between the left and the middle plots, and also why the ground state is immune to the fast oscillations.
Yes, okay. So the ground, what is going on here, right? I mean, so we're looking at the population of two different states in the atom. The ground state is the orange and the excited state is the blue. And when we look at these populations, we are really plotting the squared amplitude corresponding to those states. And those states are field-free states of the atom. Of course, the field-free states are not eigenstates of the atom in the field anymore, right?
That's
So,
correct. Yeah.
so what this is saying in a way is that the ground state remains to good approximation a good eigenstate, even though the field is there. But the excited state is strongly modified by the fact that there's a strong electric field. And it instantaneously changes depending on the sub-cycle oscillation of the electric field. So if we were to think about this adiabatically, but on the optical cycle timescale, so very fast adiabatic dynamics here going on, then the excited state will change and it will become a D wave and an S wave and polarize, and then it will go back to being a P when there's no electric field. And then when the electric field hits again, we will have it be of the other parity again. So it's changing very fast due to the instantaneous electric field. But even the remarkable thing, I mean, if I may say so, is that this is happening, but the underlying Rabi oscillation just keeps going anyway. So we have these two different time scales of physics: the Rabi flopping, which we can see here, and then these counter-rotating oscillations here, and the mixing of the 3p state really hybridizes with the S and the D Rydberg states on a sub-cycle time scale. So it is very different from the two-level system I have here to the left. This is a pure two-level system. This is a two-dimensional Hilbert space where we're driving the dynamics, and the total population is 1. So if we counter-rotate a little bit here on this state, then it must be compensated here. While in this case, actually, we're moving population to the S and to the D, and then we're moving it back to the P on very fast.
So in the middle plot, it's not simulated by a two-level model, but in a realistic atom.
Right. So
okay, I see.
Exactly. Yes. Yeah.
Okay.
But it is really changing the shape of the excited state. So one can think of an instantaneous eigenstate that we have, which is very different from the field-free eigenstate here.
Yeah. Now I get it. Thank you.
So we have also another question from an anonymous attendee. Can these photon-electron correlations manifest as momentum correlations? That is, the electron and photon move in opposite directions?
Yeah, that's a good question. We have not considered the momentum as such. I know that there is work on momentum entanglement between the photoelectron and the ion. So I would say yes. Then typically one has to look at the center of mass of motion. Could one maybe elaborate a little bit on the question there, or I think this is something that also should be done. But
yeah, feel free to post sorry to interrupt you. Feel free to post a follow-up question for the speaker. If you don't want to waive your anonymity, it's fine with us, but I think it would be great to have a follow-up question. Sorry, continue. Sorry.
Yeah, I could say in the meantime here that looking at the energies as we're doing here, I think we can pick one atom and we imagine that it's stationary, and then we do all our calculations in the center of mass, so to speak, for that system. Yeah.
I do not see a follow-up question, but do feel free to write. That's what we are here for, and we want to see a good debate.
Even battle.
Would any... Huh? Sorry?
Even battle. Who knows?
Even battle, yeah. I mean, suggestions are welcome, as I said. And this is a very hot topic because to generate coherent superpositions in the attosecond domain and qubits and qubits could be very promising in the future. And for those who are watching and are interested in quantum technologies, I mean, the coherence times tend to be longer than what we are dealing with. And that's one of the key motivations for us to look at these things. Exactly. We have one person. Hang on. Go ahead.
Hello.
Yes, hello, Anjaneshwar.
Yeah.
Welcome.
Thank you. Yeah, I'm the one who asked that question in the chat. I was actually like about the photoelectron momentum correlation. I was actually interested in it because I'm still trying to understand your work, I guess, because I'm not um, I'm not yet comfortable because I'm a new graduate student thinking about Rabi oscillations and things like that. So I'm still learning these things. But I was thinking about this correlation in the perspective of like, say, like a down conversion crystal, where you have like, where you say you entangle two different uh, lights that is emitted from this down conversion crystal, and then you have momentum correlation in the two beams emitted. And I was wondering whether, you can use, say, this atom or these atoms as a source, and then use the photon and electron that's emitted as sort of like a electron photon entanglement in momentum as well, or the momentum as they're emitted, or something like that. Would that be the right picture, or would that be yeah?
I mean, we can have we can understand the correlations by momentum conservation and so on, and they would also manifest in the quantum picture as entanglement. It's only when sort of the wave function dephases and we lose those superpositions that one then talks about classical correlations emerging from the quantum state. So I think, as soon as you have an idea about some conserved property, momentum conservation or something, and then you look at the quantum description of that, then you would have some entanglement with it. I think so. I think yes, you will have many ways of doing interesting things there.
All right. Yeah. Thank you.
Yeah.
So thank you. We have another question from Deepayan Biswas. Can this type of entanglement be extended to molecules, and can nuclear and electronic properties be entangled?
Yeah, sure. Now, in my presentation here, I didn't give a review on all the ongoing things in the community. But for instance, the work of Mark Racking here, they're using 2 attosecond pulses and then they ionize a molecule, and the molecule starts to vibrate, and then they use a second attosecond pulse to ionize again. So this is all perturbative ionization, but because the molecule vibrates, it has this kind of a molecular motion. So the state of the ion that you will generate will change over time because the molecule is vibrating. So in a simple case where the vibration is just a two-level system, then the molecule will vibrate, it will expand, and then it will come back to the original place. And if you put your second attosecond pulse exactly in that place, then the photoelectron is generated from the same type of ion state twice, and the photoelectron and the ion separate. So now you wouldn't have any entanglement. But then if you change it so that the molecule would be in two different places in its motion, then typically you would have entanglement. And if you, under ideal conditions, you could have full entanglement if you could really populate the vibrational levels by the same amount and so on, and control the dynamics. So this is another way of having complex dynamics and studying how entanglement can come and how coherences can be created and so on. So it's I would say it's super related, but the models we have and the systems we have are a little bit different.
Is that clear? Would you like to follow up? If you want to, you can unmute yourself and talk to our speaker.
Yeah, it's clear. Thank you so much. It was a really nice talk. Thank you.
Thank you. So, are there further questions, comments? Feel free to use the opportunity also on YouTube. We're going to stop the live streaming soon. So if you would like to reach out and you are a subscriber, don't forget to write your question on the live chat, and we are monitoring this, and we are going to finish our streaming soon. So do reach out if you would like to. And would anybody else like to ask anything? Or say hello to the speaker? People get quiet on Fridays, but we have so far had quite a nice discussion, and people from several backgrounds, which is great. So I don't see anything on YouTube. So we are going to stop the live streaming now. So if you're watching on YouTube, thank you for joining. Have a great weekend. And we are going to go offline. And we thank again Professor Dahlström for this really interesting talk.
Yeah, and thank you, Carla, and thank you everyone for your questions and for your time. This is really a wonderful occasion. Thank you.